One more time, good morning. I'm Guilherme Gusmão. I'm representing the Techography Institute of the Catholic University of Rio de Janeiro. And today, I'll be talking about treating dataset imbalance in feral echocardiography classification. Feral echocardiography is a mainstay in cardiovascular imaging, as it is a non-invasive and fast method. Using ultrasound transducers, it can generate grayscale videos that contains enough information for a doctor to make evaluation about the fetal's heart conditions. The first step in this evaluation is the identification of the feral cardiac views. These are standardized imaging planes defined in the medical literature that brings valuable information about the development of the valves, vessels, and chambers of the heart. As you can see here, some examples. We have the basic four-chamber heart view, going to the more complex left and right ventricular outflow tract, and the three-vessel trachea view. These are very important because it's through these views that a doctor can make comparisons and seek for abnormalities in the heart structures, like congenital heart diseases, the cause of many stillbirths. Many researchers are trying to automate this process, as it is a very hard and time-consuming work, prone to misclassification. One trained solution is the use of deep learning for echocardial classification. This entails the use of a convolutional neural network fed with a dataset containing images obtained from the frames of different echocardiography videos. And after the training, the model is able to make predictions about the ferocardiac view of unseen images. One obstacle in this type of solution is the data sets, as they can be very scarce and small. And beyond that, they can be highly unbalanced, meaning that some classes are more prevalent than others. As an example, we have the class distribution of our data set. And as you can see, the 4CH and 3VT classes are more present than the other classes. When trained, this can cause bias toward those most represented classes, and the model can gloss over the underrepresented ones. So for our problem, we try a data-centric solution where our primary effort was refine the coarse data set by pruning, organizing, and augmenting it where is needed, instead of trying to take a model and make it deeper or wider, or to find more data. To better understand this, we are going to follow this roadmap, going through our data set, then the architecture, the additive experiments we did to better understand the impact of these methods, the results and final conclusion in future works. Our data set comes from it's private and comes from a third party. All the patient information were anonymized, and it's containing annotations with the ground truth of the ferocardiac views, and from the echocardiography videos, we obtain images from the breaking up the frames of these echocardiography videos. For our architecture, we chose to use the EfficientNet, as it is a state-of-art model for image classification. We were already familiarized with it, as we were using it in other projects in the institute, and it's scalable if you needed to. We opted for AIDEN and use our S-loss categorical cross entropy, as our problem is a multi-class classification problem. Well, for our first experiment, we just want a baseline to see how the model would behave with the course data set. We tried first with all the data, but as was taking too long to train, we had to take only 10% of it. From this 10%, 8% was used for training, and the last 2% were used for the validation set. And as you can see here, we preserved the imbalance in both sets. As expected when training, the model overfitted really fast, and as you can see, it was not good enough for generalization, as the model had problems predicting the validation set. We can see here through the confusion matrix, where the diagonal shows the correct predictions, that the model became almost a coin flip. When he tried to predict the images from the underrepresented classes, most of the time he thought it was a 3VT or a 4C8 classes. So after this experiment, and with a better understanding of the data set, we tried to apply a combination of preprocessing methods. They are stride, shuffle, and stratify the batch. First, because we are working with a echocardiography video and take frames from it, many of these frames, as they follow one another, can be very similar. So we applied a stride, take one frame every 5 frames. So with this, we were able to take a great volume of exams from a variety of patients, increasing our data diversity. And only after the stride, we applied shuffle to guarantee that we were not locked upon a bad batch. Finally, during training, we use a stratified batch, where instead of fitting all the images at each epoch, we chose a fixed number of images, chose randomly, so that at the end of each epoch, the network was exposed to the same number of images for each class. The idea behind this was to reduce this bias. As you can see here, now the features learned during training were more helpful for predicting the validation set, although our accuracy was reduced. We can see this better here in the confusion matrix. The bias was reduced, but the model, as it has now, now that you understand there is more options to choose from, he starts to have more difficulties to make the correct prediction. So we were after a lot of thought, we decided that what was missing was we needed more images from the underrepresented classes. So we applied some augmentation techniques to increase this number, which we opted for applying rotation and brightness. In rotation, we applied a turning with random angles, and in brightness we implement multiplicative brightness to change these images. Why we opt for these ones? As we talked with a cardiologist, we cannot apply too much transformation, or we could end up with a very unrealistic image to train the model. So after this, we apply only the training set, as we wanted the model to be exposed to more underrepresented classes. And finally, we converged. Our model converged, and our accuracy increased highly. As you can see here for the confusion matrix, our model was finally able to have a better generalization, and the quality of the predictions got higher. This can be seen here through the F1 scores. During the first experiment, we can see the bias towards the most prevalent classes, and almost no correct predictions of the less represented classes. Then in the second experiment, we reduced the bias and lost accuracy. Then finally, in the last experiment, we have a jump for the underrepresented classes from 0 to more than 80 F1 score and a better prediction. We can conclude that if you take our time to better understand our data set and apply the right methods, like reduce redundancy, increase diversity, we can bring balance to an unbalanced data set without the need to go deeper or wider or find more raw data. There's a lot of potentials here and many other techniques that could be applied to combine the methods present here. We could, for example, use transfer learning, applying techniques like feature extraction and fine-tuning to try to surpass the accuracy we reached here. We could use a weighted loss function to punish the misclassification of the underrepresented classes. And we could add explainable artificial intelligence to bring more transparency to the neural network's black box nature, as it is an issue in the medical as it is an issue for the professionals in the medical area, as they feel uneasy about how the AI models are taking decisions. Thank you for your attention. Hope you like it.
Thank you. Of course, we like it. So we have time for questions. I noticed that there are not many questions when the conferences are online. So I've got quite a few questions actually while listening. But for example, how big the data set needs to be for this task? Because if it turns out that not that big, but I think it's not the case, then maybe just augmentation or just pruning would be enough. But actually, what's very interesting to me is you said that when you have adjacent frames and you sample them, they can be very similar. The images can be very similar. So I was wondering whether maybe you have some metric for similarity. If yes, you could maybe use active machine learning techniques, for example, when you have such metrics, or maybe just the observation and you don't have like formal metrics. Oh, I see one question, so that will be the next one.
Okay. Well, it was we pruned ourselves these similar frames, so it took a lot of time. But indeed, if we had a metric, it could improve how we eliminate these frames. There's a lot of you can do. There's many different ways to prune this data set, and what is the main issue? The 48, for example, we have a lot of data, but we have too few of the underrepresented ones. As most of the time, these classes only appears in rare occasions. There is specific structures or conditions that the doctor is seeking for. So if he doesn't need to look there, there will be no data. For example, most of the work that I find only try to see if it is a 48 or not. There are some others that focus on 3VV, but for our project, we needed to identify that 5 different classes. So it was an issue, even with augment. And when we try only augmentation, the results were not good. When we tried only pre-process, it was neither good. I hope I could clarify this.
Thanks a lot. I see a question. Marcin, can you ask it, or maybe I have to unmute you?
Yeah. Oh, yeah. I can.
Yes.
If you could please go to the previous slide with conclusion, that will make it a little bit worse. So one thing you've postulated that may at least partly cure the limitation of the size and variety of the data set. You mentioned that you may use transfer learning, but I was wondering because in other typical medical domains, there are reports, for instance, about problems with transfer learning caused by very basic things like that in one clinic, for instance, the data was collected with, let's say, General Electric machine. And in other clinic, that was a Philips machine, and another clinic that was a Hyundai machine. And it turned out that transfer learning from one of those of the set to the other actually required quite an amount of additional work on standardization in a way, which was also very not obvious. Do you think this may be also your case?
Really, I don't know. The data set comes from different machines.
Okay.
So I don't, and as it was all anonymized, I can't say correctly which machines were these exams. So we are already exposed to different machines. But the idea behind this is because this work here is only a small piece of the pipeline. When a doctor makes an evaluation, he identify these vistas, then he can start to make annotations like segmentation, cardiac phase. So, and for example, in the segmentation part, if you use pre-trained, if you use efficient net with the pre-trained ImageNet weights, we have great results. Although they are, as we know, from what we know, ImageNet has nothing to do with medical images, but it works. It simply works.
Okay, thank you.